company has 15 managers, of whom 7 are women. It has 128 other employees, of whom 45 are women. And we want to select 2 people with replacement. Find the probability we get a woman and then a manager. And so the probability here is, first we get a woman. That probability is 52 out of the 143. Remember, the word and, when we select more than one thing, means multiply. So we're going to multiply that by the probability of getting a manager. Now the problem says we're doing this with replacements, so whatever woman we take, whether it was a manager or not, goes back into the sample space. So now the probability of getting a manager is the 15 people out of 143. So that's the first probability. How about the probability of getting a woman and a man? Again, n is more than 1. We're selecting more than one thing. And means multiply. Probability we get a woman is again 52 out of 143. Now the problem we get a man is the 91 out of 143. So that would be our probability there. Now, what's the probability we get both of the same gender? And here's where that idea of rephrasing with and or comes in. What are the 2 ways we could get the same gender? Well, we're looking at the probability we get a woman and then a woman, or the probability that we get a man and then a man. Now, the word or means add. The word and means multiply. So what we're going to do, the probability we get a woman the first time is 52 out of 143. Probably get a woman the second time, knowing that we did this with replacement, is also 52 out of 143. Or, so that means we can add this situation also, which would be the probability of getting a male, which is 91 out of 143, times the probability of getting a male, which is preserved at 91 out of 143 because we did this with replacement. But what if we did this without replacement? And you would tend to see this word, this adjective. We'd say, hey, we're going to randomly select 2 different people. Well, now how does that affect things? Well, if you come back to this situation right here, what's the probability we get a woman and a woman? Well, the first time we got a woman, the probability was 52 out of 143. Now, we must have had a woman the first time, so what's the probability the next time we get a woman? We don't know where that woman came from, manager or other, but we know this was depleted by 1, and then this guy is also 1 less, so the sample space shrunk a little bit. So now what do we have? We've got 52 out of 143 times 51 out of 143. Likewise with the male, we started with 91, but if we took a male and couldn't replace him, then it's this right here, so add those 2 together. If we're looking at the multiplication rule itself, the way we would write this for, let's say, the probability that we get a woman and then a man, we would say, okay, what's the probability we get a woman and then a man? And that would equal the probability of getting a woman times the probability of getting a man, given that a woman was selected the first time. That clearly is a W. Whoop, right there. Okay, so how do we do this? Well, probably the first person was a woman, was the 52 out of 143. And now we again would say, all right, the women were depleted by 1. We have 142 people left. So now what's the probability we get a male, knowing that the woman was selected without replacement, and so that these are the quantities that we have in each category. So now it would be the 91 males out of the 142 females. So understand the multiplication rule, understand that this means given, this is a conditional probability, and understand that when we see a thing like the probability that both are same gender, we can rephrase and would mean multiply because we're selecting more than one thing, and or always means to add. And then finally, if we're doing a problem, we're going to get more into the conditional probability, but basically we'd say, hey, what's the probability that you would get a woman knowing that the person selected was a manager? And instead of going into any crazy formula, all we have to do is shrink the sample space. Recall that originally we had these totals, this marginal distribution, we had 52 here and we had 91 here for a total of 143 people. So now what's probably get a woman knowing that a manager was selected? Well, we shrink the sample space down. we no longer have these as our possibilities. We only have 15 managers that could possibly be selected, and out of that, 7 of them are women. So the probability would be 7 out of 15. We can also write this then as the probability we get a woman, knowing that a manager was selected, so knowing that the person was a manager. Let's try one more. What's the probability that we get an other employee given that the person selected was a man? Now, in this situation, we're only dealing with n is 1. We're just selecting one person, and they must have both these characteristics. We want to find the probability we get an other employee. Well, if there was no other information given, that would be 128 out of 143, but it's not. We're told what's probably get another given that the person was a man. So now, even though there's only one person selected, there is one characteristic we know for sure about this individual, that they must be a man. So now we're just down to this sample space that has 91 people in it. Now, out of those 91, 83 of them are other employees, so our probability would be 83 out of 91.